or on this computer. So in 62, what was the situation here? Let's see. Okay, so in problem 62, let me copy this. Okay, let's you have okay, so here like the idea is you have to think that the particle, you have a particle with a velocity, and each entry, each component of the velocity is some sort of random variable. So if you want, you can write them even in uppercase, because that's like usually our notation for random variables. So each entry here just refers to like the velocity that the particle could have. um yeah, so this one, I suppose it's still, it can be done. So it like, okay, so there's this sigma, let's, sigma is, you, in this case, is root of kt over m. So I'll just write everything in terms of sigma, because otherwise it's a little bit of a mess. So they're saying that the density function for v, for the velocity is just 1 over 2 pi sigma to the 3/2 e to the minus, okay, so, and this is going to be, okay, good. Right. It's some, okay, so if you look at it, it is very similar. I'm again, I'm just rewriting every the formula in terms like what they wrote for sigma. If you look at it, it is very similar to the usual Gaussian that we wrote in class. It's just that the Gaussian that we wrote in class was for like a function of one variable. This one is kind of like a function of three variables, so that's why I don't know if you remember, like the formula for the Gaussian in class has had like a square root, and this is like 3 square roots, right? That's why there's like a 3/2, and that's just because there's one Gaussian per direction. It's just that they are all being multiplied together, if that makes sense. So this density is actually the product of 3 Gaussians, one for each direction of the velocity.
I see now. Gotcha.
Is that making sense? So this
Yeah.
is, it's a product of Gaussians, actually. It's actually more explicit if you remember that the length of V is just like the length of V squared is like V1 squared plus V2 squared plus V3 squared. So when you put this into here, then you see more because like, you know, the when you have like a sum in an exponential, it's like just a product of exponentials. You can see more clearly that it's like a product of of Gaussians. So there's like a Gaussian for each direction in space. That's kind of like this Boltzmann distribution or Maxwell distribution for velocities, which is kind of famous. So okay, so here's like the problem. The first one is that they're giving you you want to go over both, right?
Oh yeah, I appreciate it. Thanks.
So the first one is that they define the kinetic energy, right, as 1/2 mass times velocity squared. That you should think about it as a random variable. Okay, so you can find its expected value, right? Remember the expected value. This is like a function of you know, this is like the function of v, right? Of the, I mean, like if you want to write it more explicitly, you can write it as 1/2 of m times v1 squared plus v2 squared, right? Plus v3 squared. So it is like similar to what we have been writing so far. It's just that in the notation that we would have written before, like in the previous notation, we would have written with previous notation, it would have been something like k equals like, you know, 1/2 m of x squared plus y squared plus c squared. It really works the same way. It's just that in this case, like the variables, is more natural to think of them as a velocity variables. So that's why you want to still call them v1, v2, v3. So so there are like a couple of ways to find the expected value of the kinetic energy, but the easiest way to do it is with this Lotus rule, like the law of the unconscious statistician. So what So what did the Lotus rule say is like, it said like the expected value of a function of a random variable is just the integral of g of x times, the density function of x dx. Okay. Now, what is g of x in, I mean, again, it's just, kind of getting used to the new notation here. G, like the function, like the 1/2 of m doesn't really matter. What you really have to pay attention is to this like expression. So like the g of v1, v2, v3 is like, v1 squared plus v2 squared plus v3 squared, right? So really, the expected value of the kinetic energy would be 1/2 m times the expected value of v1 squared plus v2 squared plus v3 squared. Okay, and how do you compute this expected value? That is 1/2 of me, the integral of v1 squared plus v2 squared plus v3 squared times f of v dv. So notice that I'm writing like a triple integral because like there's one for each direction. Is that making sense?
Yeah, it makes sense now. I'm just assuming, so would it be hard to like compute the integral then?
Oh, no, actually, it's actually going to be easy. I mean, kind of relatively easy because like it is like a Gaussian. So it will be, I mean, like the thing is like in these bounds, like, I guess, didn't say it explicitly, but it is assumed like, each of the V's, like, EV is like going from minus infinity to infinity. So like, it's like, or at least that's like how it was being, yeah, it was meant to be. So really, you have to compute 1/2 me. Like what's going to take more time is actually just to write everything. It's going to be v1 squared plus v2 squared plus v3 squared, e to the minus, let's see, 1 over 2 pi sigma to the 3/2, e to the minus v1 squared plus v2 squared plus v3 squared over 2 sigma squared. I mean, just for I guess I included this one in the list of problems, but just because I thought it was an interesting problem to look at. But actually, I mean, it is a triple integral, so although like I will only ask single or double integrals in the exam because like we didn't go over really do examples over triple integrals. But at least I can tell you how to finish it because it's like an interesting question. Like it's just that I thought, okay, yeah, it's like a very classic problem. So what? Oh, sorry, there should no longer be an e because that was for expected value, and I got rid of. So, but yeah, like triple integrals, I guess, like we didn't really do any examples in class, so I wouldn't ask that. So one way, I don't know if you remember, think of this as like literally like, you should think of this as being like x squared plus y squared plus c squared, right? And these are like x squared plus y squared plus z squared. So I don't know if you remember, like when you integrate something that has x squared, y squared, z squared, like easiest thing is to go to spherical coordinates, right? That's like, that was the easiest thing to do when doing like an integral in
Oh, so that's like rho square.
right, exactly. It's like okay, so perfect. So it is like a rho square. It's just like it's with different variables, but it really all works the same way. So it is like a rho square, perfect. Then this doesn't change at all. It is like a rho square, and then this is like e to the minus rho squared over 2 sigma squared. And then dv, if you remember, I mean, again, that's why I'm not expecting anyone to remember like a spherical, but the dv in spherical coordinates, like the usual conventions in Calc 3 was like rho squared sine of phi, right? D rho, d phi, d theta. Okay. And what are the bounds for this integral? The thing is like the theta, if you remember in spherical, it would go from 0 to pi. The thing is like this integral is actually taking place over all three-dimensional space. So the theta goes from 0 to 2 pi. The phi in spherical went from 0 to pi. Those are easy bounds. And the rho goes from 0 to infinity. In this case, because it's like an improper integral. So this is an integral that you have to do in spherical. Is that making sense?
Yeah, it makes sense, man.
Okay, and then like how, like if you wanted to do this integral, let me just like simplify it a little bit and tell you how you could do it. Notice like actually this integral is easy to do. In like all the interesting stuff is really with rho. The sine, the phi stuff and the theta stuff is actually easy. So when you integrate theta, you get 2 pi. So you can even put it here. So you could put times 2 pi. That's what you get when you integrate theta. And when you integrate sine of phi d phi, what is sine of phi d phi? That's minus cosine, and then like that, they'll give you a 2 because of the bounds. So you get a 2 here. So it's really just boils down to an integral from 0 to infinity, of rho to the 4 e to the minus rho squared to sigma squared over 2 pi sigma to the 3/2 the rho, right? And that one, there are a couple ways to do it. One way would be there's like a way which would be like one way to do it is kind of like by integration by parts, because you do not like if there were no if there were no rho here, you kind of know the value for this integral because that's kind of related. It's more or less the essential, almost like the expected value of the standard of a Gaussian. You have to play a little bit with it to compare it, but it is not too different from that. So you can kind of relate that to that expected value. The other way to do it is kind of like doing this Feynman trick, if you may remember this one. So let's see, if you take the derivative with respect to sigma, of
Professor, quick question. Outside the integral, it should be 1/2 m times 4 pi, right?
correct, yes, right. Oh, I get you. So that this one should be a 2, you mean? Yes, thanks.
Yeah.
Yeah, thank you. So right, like the only thing I was saying is that if you do this Feynman trick, which is actually useful, that's kind of how we found the moments of the Gaussian, if you remember. You will notice that if you take the derivative of this, let's see, is this going to work? Because it would be, yeah, if you take, it should be related, right? It will be something like, I mean, you have to kind of like, you have to play a little bit with it, actually. It's but I mean, when you take the, for one, okay, this is like actually a little bit like a long integral. So because what I'm, at some point, like it's actually just better to go back to the formula I had given for the moments of the Gaussian. Where is this moments of the Gaussian? Let's see. I mean, it does involve like the second derivative with respect to sigma. It's just like it's a little bit long because you have to do like a product rule and other things. So it's maybe a little, yeah, it's just like a fun problem, but it is definitely long. Where is this? Where did I write the Gaussian stuff? Oh, here you are. Where is this Gaussian?
It was like e to the t squared over 2, right?
Well, that was the moment generating function, correct? Here I'm just doing like the regular integral, which is I mean, it's not quite the same. No, what the one that I'm looking for, let's see. Oh, here we finally. So you see, like here, like we had computed like this integral, and then we kind of did it for the x squared case, right? Doing this Feynman trick, and then I wrote the expected value for x to the 2m. So here you kind of are going, you can basically, if you wanted, you could just put m equals 2 in this one, and that more or less gives you like the, like it is twice, more or less it will be related to this fourth moment of the Gaussian. Up to some constants, this is essentially the fourth moment of the Gaussian. That's what I'm trying to say. It's just that you have to play a little bit with the constants. But what I was saying earlier is like, this is like a triple integral. So it's not a problem that I would ask. I just thought it was like an interesting problem because it's like a very classic problem. But it does require spherical, so I wouldn't ask it. I just included it in the list because I thought it was fun. But yeah, you should compare it to, so you can ignore it if you want to, but for the Gaussians. But I mean, this is like, you know, like again, like up to these annoying constants. Like if you pull out all these constants from the integrand and just write like x instead of rho, that, like, you know, that is something like you can get work using integration by parts or things like that. So it's just like a little bit, it is a tedious process, regardless of how you want to do it. So I wouldn't worry too much about it, but I thought, okay, this is like a fun problem. And then, is that making sense? So
Yeah, makes sense now. Thank you.
Yeah, no, but it's like, I mean, it's like it's a nice problem, just because again, like this is like the standard distribution for like an ideal gas. Like it's kind of like the distribution for velocities for an ideal gas. I can tell you that the answer, I mean, if you want to check it, just to give you what the answer is, like the answer is going to be that the expected value of the kinetic energy is 3K, the Boltzmann constant times the temperature over 2. So which you think about like 3 times kVt over 2. So kind of like this is sometimes what's like the energy per degree of freedom of the particle or something like that, but at temperature T. But yeah, I mean, it's a long problem, so I still recorded it just in case like someone showed up later if they want to hear how it goes. But definitely in the exam I would only ask single integrals or double integrals. So I think this is on the PDF maybe the only problem that had like a triple integral. So don't worry too much about this one.
What about part B? What's the answer for that? Can you write the answer?
Well, the answer, it is like written down on the PDF, right? It's just that like if you look at part B, what you have to do is like kind of compute the probability that this one was asking for the density function for the speed, right? Like that's what you want. You want the density function for the speed.
It said the probability.
Oh, right. But yeah, so okay, that was a misnomer. I mean, in that case, I mean, you could, once you have one, you can get the other. It depends. Is that like if you look at like the formula below, it has little f, and usually little f is like the notation I have been using for density functions, right? So that's, but yeah, I could have said like the density function. In that case, it's just like you ask for the probability that the speed is less or equal to some value, right? That's usually how you find density functions. And again, that will be this triple integral in spherical. It's just that so it's more or less like very similar to what we were doing. It's just that this would be the probability that the speed squared is less or equal to v squared, you see? So when it is kind of like the same triple integral that I wrote here. It's just that one of the bounds, you know, one of the bounds is going to be instead of like this bound being from 0 to infinity, this bound is just going to be from 0 to v squared. That's the only difference. So everything else doesn't change. Nothing else changes in this problem. So let me write it here. So like the only difference is that this integral will go from 0 to v squared. Let me put that here. And so the density function for the speed is the derivative with respect to v of this probability. But that is, you know, like a typical fundamental theorem of calculus type problem. So you kind of you can do it that way. Let's see. This is okay. Oh,
Yeah,
right.
makes
So,
sense.
so the only difference is that this is like a probability, so it's just like integrating the density function. So this, like, instead of like being rho to the 4, it's just rho squared. And so I think, let's see, is this going to be fine? Yeah. Okay. And then let me see. Am I going to right, because this is like the this is like the probability that oh my god, I'm so okay, so silly. Okay, this is like v1 squared plus v2 squared plus v3 squared less or equal to v squared. So like it is a sphere of radius v. Okay, so it's just v. Oops, sorry about that. So this probability is just like a sphere of radius v. I don't know. It may have been better just to leave it like that. So you can see, like, when you take the derivative with respect to v of this, it's just literally replacing v squared here by the fundamental theorem of calculus and v squared here. And that should just more or less give you what's on the PDF. So this one was a lot faster, but still it requires doing the trick of switching to spherical coordinates. So you don't have to worry about it. But that's kind of how you got it.
Yeah, I see it now. Thank you.
Yeah, sure. Okay, cool. Yeah, we can go over any questions. I don't know if there's any other ones that you want me to go discuss. How's everyone doing? Oh, right. By the way, the final, yeah, so it's on Wednesday. I will do 5 problems on each part. At the end, I decided just to, but one at least should be, I'll make sure that each part has like 1 or 2 problems, which are like, I mean, I don't want any problem to be particularly long, but I'll try to, you know, make sure that you have enough time. Each part will have 80 minutes, so is less than twice the number of problems before, but that you had on the previous midterm for like twice the amount of time. But I mean, it should be fine. And I'm trying to avoid like any long like integral calculations or something like that, so you don't spend too much time computing things. But yeah, I think it's better. It's just easier for me to do it 5 and 5 because like the exam is just 150 points, and then so that way I just make each problem 15 points, and that just seems easier. But just as a heads up, because I remember like the PDF said like either 4 or 5, but I think I'll just go with 5 because of that. Yeah, is it okay? Have you had a chance to look at the problems on the PDF or the practice problems?
If no one's gonna speak, I'm just gonna say 81.
Yeah, if you want to ask another one, yeah, we can go over that one. Oh, 81, you said? Or which number did you say?
Yeah, 81.
Oh, right. I think you can, yeah, this one is a useful one. So this one is nice to see. So 81, so X and Y are, I'm just writing it in case like you are looking at non-updated version, but I haven't made changes to the PDF in a while. But so here X and Y are uniform random variables on 0, 1. Okay, so it has 2 parts. Part A was to find the density function. By the way, that one had this one. Oh, this is good that you are asking me about this one because I did have a typo on this problem. So there was a typo here. I'll say what the typo is in a moment. Then find the density function of u equals x and v equals x plus y. The typo was here because in the PDF I had written y equals x, so that was a mistake on my end. So here there was a typo. And then part B was to compute the density function of just V. And here, like I think it should say joint, which is on the PDF, so that's okay. Just in case, I should mention that I mean part B actually we already know how to do independently of this problem because in part B it's literally just a convolution. You know, the density for the sum was just a convolution, right? So I should just say that these we already did before. So the density function for V is a convolution, right? Of x and y. And actually, I did find the convolution, I think, for the two uniform random variables when we talked about this convolution. So it's the part B we actually already did in class, so you can check that part either in the video or just the PDF. It's just that on the PDF I had called this Z, but instead of V, but it's like the same idea. But part A is an interesting problem because
So it'd be like f sub x times f sub y of x
right.
and v minus x or something like that.
Yes, it was in this in part B it was like what we would call f of b was f sub x star. I mean not time, I mean it is times, but it's like this weird multiplication, right? You can call it v, which was like the integral from minus infinity to infinity of f sub x times f sub y. But then this one got shifted, and I guess it has to be like v minus x dx. Yeah, so where did we do this? It should be like 1 or 2 classes ago. I think maybe 2 classes, I don't remember. Where is it? Ah, here it is. Yeah. Right. In fact, we did the exact same interval. So it's like, yeah, it's here. It's just that again, I call this Z, but it's essentially this formula. So, but right, like that's like that was the formula for the convolution.
How do you get f sub y of v from for the density function from the integral?
Let's see. Could you repeat that question? I don't think I heard you well.
So you know how you wrote the density function as f sub x convolution with f sub y of v. So is that just like a notation type thing? Like how do you?
Oh, right. You mean yes, this part is just like a notation type thing, correct? Like you can skip this part and just jump right ahead to the integral formula. I'm not sure. Let me check if I gave you that one on the. If you check the study guide, there's like a list of formulas that I said I was going to give on the the exam, let's see, let's see, did I include that? Okay, I'll did I say, okay, I think I haven't included it, but I'll include that one on the exam, like the convolution. Yeah.
Yeah. So in the formula that you gave us, it's like f sub x, but they're like both functions of z.
Right, let's see, where did I have this one?
Oh, so there's a parentheses on both of them. Oh, I see.
Right. Yeah, no, but I mean, I did write it on the story guide, but I didn't write it on like the list of formulas that I was going to give you. But I think I mean, what I'll give you is like the integral. I won't tell you what it's for, but then you just have to remember that that was for the convolution. But yeah, I mean, I don't mind. Yeah, I'll give you this formula for the convolution. So I'll write it like as like what I'll give you is something like this. And then you just have to remember that that's like what you use to compute the density of a sum of random variables. But that's okay.
So
I'll
on this one, if we apply the fundamental theorem calculus, right, on part B,
well, that's actually how it came from. If you track down the steps to find the it's kind of
so
uh-huh.
yeah, that is a density. Yeah, I got you.
Correct.
I forgot. I'm sorry. Yeah.
So let me just make a note to myself to add this formula before I remember. I forget it. So just give me a second. Sorry. Otherwise, like it will skip. I will totally forget it, and I didn't want to include it. So I'll put the formula for the convolution. Okay, cool. Yeah, so part B, I mean, it's an interesting problem, but like we did do it before. Like what we didn't do was part A. Okay. Where did I leave my here it is. So let's talk about like the joint, like so what we want in part A is the joint the density function of U and V. We want this. So remember what that means, like that a joint density function means two things. This means two things. First, like any density has to integrate to one, right? When you integrate it over all potential values. So like the first condition is always, I mean, which you know, it's like kind of like a given. It's not, that's useful when, you know, like you're given like a function and you're asked to find like the value of a constant that makes it like a density function, like you integrate it and force it to be equal to one or something like that. But so that's like you know, that is like the first condition, like for a joint density function is that, and then the second condition, which is more useful for how we're going to compute this, is that the probability, let's see. Like if you remember, like if you had like a region in on the XY plane, well, in this case it's a UV plane because like the variables are U and V. So here's U and V. The property of like the joint density function is that the probability that U comma V is in this region is just like the integral, the double integral over this region of F of U comma V of UV dV du. So it looks a little bit like weird. It sounds a little bit weird, but it's just saying like the point of the joint density function is that it's what you use to compute probabilities. Okay. In practice, this should work for an arbitrary region on the XY plane, or in this case, a UV plane. So this is like a property of the joint density function, regardless of the region. What's useful is that you can take the region to be, you know, if you remember, like analogous to how you found the density. How is it that we would find the density for a function of one variable? Oops, I already went through this part here. Oh, like when we had like just one random variable, the way we found the density was like you would look at this probability and the random variable is less or equal to to some value. So we can do the analog for that here. So in particular, just take a very specific type of region, which is like kind of like if the region R. So let me try to draw it like this. Here's U, here's V. So imagine that you have a value A here. Let's call them A and B to not make a mess. So I'm going to look at kind of like this semi-infinite rectangle. So my region is going to be the places where the random variable U is less or equal to A and B is less or equal to B. Okay, so what that means is that the probability of U comma V being in this region, it would be the integral from minus infinity to U, sorry, minus infinity to A, because I'm calling this lower upper bound A, and then from minus let's see, we just okay, I will improve the notation right now just to make it more similar. This if you have noticed, like a lot of like this course is just like finding the right notation. It can be a little bit tricky. So let me write it like integral from minus infinity to U minus infinity to V. The property of the joint density function is that this should be the the integral of the joint density function. The thing is, like, it is better to avoid calling these U and V again, but the easiest way to fix that, if you want, is call them U tilde V tilde or U prime V prime. It's just that here prime doesn't mean anything with derivative, just means like, it's like a dummy index of integration. So we can call them like, I'll call them U tilde V tilde because I don't want you to get confused with derivative notation for if I put primes. Okay. So that is what this would be. Is that making sense so far? So good. I'm just saying that we will study how this behaves. We'll study how this behaves in terms of X and Y, and that's how we will find the density function. So far, so good. Any questions about this?
Can you explain where did the tilde come from? Like why you put that tilde?
Where this came from?
No, like the tilde, like you said.
It's just okay. It is you have to make a decision somewhere. So one option was to one option was to call like instead of like what I'm trying to talk about is like kind of like the probability that U is less or equal to U and V is less equal to V, right? You could have called this like bounds A and B, but I have just in analogy with the case of one variable, I'm calling the bounds like the same letter as a random variable. So that's why that allows me to put U and V as as a bounds for the integrals. The thing is that it's more like of a aesthetic thing. It's just that since you're using already U and V as the bounds, it is not convenient to put the same letter for the variable of integration. So you could have called this T and S or something else. It's just like it can get confusing. So I'm just trying to call this like U tilde V tilde, just to remind you that it's related to the U variable and the V variable, but I'm just trying to avoid using the same exact letter, just to give you like an idea, it is similar to saying that, like, imagine like f of x, like the density function of x was like x squared over 2x squared on 0, 1. That does integrate to 1. So like if you were to write like the probability that x is less or equal to x here, that would be the integral from 0 to 1. Well, sorry, that's integral from 0 to x. And so the question is, do you want to put 2x squared dx? I'm just saying that it just looks a little bit odd because x is already here. So that can be a bit confusing. So my way to fix that is just to call this x tilde. You could also have called this x prime. It's just that then you can get confused about prime being there. Is that making sense? So it's just so that I can keep the x on the top the variable on the top. And so I just fixed the variable of integration by calling it something related to the variable that I care about, but with a slightly different number, with a slightly different name. Is that making sense?
Yeah, yeah. Makes sense.
So it's like, I mean, there's different options. Like, for example, you could also have called this 2t squared dt. It's just that it's not it's not great to just use like a completely different letter. It's better to have like a letter that is somehow related to the names for the random variables. Is that okay?
Yeah,
So
yeah.
this is an aside, like just like to explain where the notation is coming from.
Mhm.
Anyway, so the point is that this is the key property of the joint density function. But now the idea is to work out this probability in terms of x and y. So let's just focus on this probability in terms of x and y.
Professor, I have a question.
Yes, yes, yes.
Since we have a formula for u and v,
Mhm.
can we do like what we did in Calc 3 and do a change of variables by computing the Jacobian?
Okay.
And then replacing dv du with the x dy?
That's where we're headed. I'm doing it in a slightly more down to earth way because I didn't really use many. I mean, I didn't use any examples where except one problem where, like, you know, if you remember, it was a kind of like a polar problem, but it was not even quite that. So because I didn't go over, there is like a formula which is basically what you're saying, involving the Jacobian. I'm doing like a more like, you know, baby version of that without remembering what the Jacobian is, but it is more or less equivalent to doing this Jacobian method. If you check the book, the book does give like a formula using the Jacobian. It's just, you know, I had to, that's one of the topic. It is an interesting topic, but I was like, okay, this is too much. So, but yeah, it is what you're saying. But in this case, it's simple enough that you don't have to remember the Jacobian to do it. So that's why I chose this problem. But it is like the same idea, basically, secretly. But yeah, there's like a more down to earth way to do it because this problem has the advantage that one of the new variables is the old one that kind of like circumvents having to find the Jacobian. I mean, it's just like the Jacobian is super easy because it's like a upper triangular matrix, basically. So the determinant is just like the product of the diagonals. So, but yeah, so no problem that I'll give you would require the Jacobian, but yes, there's like like, you know, problems. Some of these problems could be more complicated problems would require the Jacobian method to kind of solve them. It's just that the Jacobian is one of those topics that, you know, is once you start getting towards like the end of the course in multivariable calculus, I feel a lot of the topics just go so quickly. So I, you know, I feel up to polar is okay, and then the course just like goes super fast mode. So I try to avoid like things that would require more than polar coordinates in this class. But yeah, it is exactly what you're saying. Now the thing is like u equals x, so that's the first you know, this one is easy to change, and then v is just what is v? V is like x plus y, right? And that's just like the probability that x is less or equal to u and y is less or equal to v minus x. Okay. And this is an integral that a double integral that we can compute in terms of the density function, right? In fact, like the formula that I will give you will not require the distributions to be uniform. The only part where that's going to be used is in part B. So it's actually useful to just write the formula in full generality. So if you look at this, let's see, what is this region? And what is the line y equals x? Well, maybe I will use at some point that the density function is Okay, let's see. So you want x to be less or equal to u and y to be less or equal to v minus x. So I mean, like I'm drawing it in a situation where like both are positive, but that's just for like, psychological purposes. That's not like a big thing. So is this region of integration? This is fine, right? Like the integral would look something like this. And so secretly, I am doing what would correspond to, yeah, like when you draw like a region in the UV plane and the XY plane and kind of like doing the same here without saying, but I'm telling you right now that that's what I'm doing, but I'm doing it like in a more like step-by-step way. And again, just to not do like a huge mass, I'll call this x tilde, y tilde. It would be less necessary in this case, but still, dy tilde dx. This is sorry, the zero intensity function, so it should be having f comma y. Is that making sense? So far, so good. Questions about this? So it was just like the important idea was just to relate these inequalities in terms of the original values, in terms of the original variables x and y. So it becomes this. Okay, so we're almost there. Let's just make a change of variables. I'll make yeah, like I'll make a change of variables. T, which will be, I think, what do I want? Let's see. Right. I mean, it's kind of silly, but here's the thing. Remember, like when you're doing these integrations, when you're doing this integral, let me put like this to emphasize it. When you're doing this integral, x tilde is like a constant, right? Like you're just integrating with respect to y or y tilde, what I'm calling y tilde here. So you can make a change of variables, which looks like a change of variables that depends on two variables, but it's actually only, I'm going to do it inside this integral. So it's only going to depend on one variable, y tilde, because x is a constant. So that means I'm just trying to check that this is like the correct bound. Yeah. So this is just dt equals dy tilde. The important thing again is that here like x is like a constant because in this change of variables you're integrating with respect to y tilde. So if you do that, this looks like the integral from minus infinity to u of what integral? This is like the integral from, I mean, yeah, so the minus infinity doesn't change at the bottom, the bound doesn't change. But when you change the upper bound, right, what happens when the y tilde is v minus x? Oh, so let's see. Sorry, I could have done like x here. I mean, that also works. Yeah, that's what, yeah, this is fine. So you could have done this as v minus x. Now it looks better. So when y tilde is v minus x, the x's cancel. And so this gives you the integral of t. But y tilde is t minus x, so yes, this. Oh my, okay, this is fine, but somehow, okay, this is fine, but it just did introduce, okay, because this is so silly. This is like really like the X tilde and Y tilde axis. Okay, so yeah, this was X tilde. This is so stupid. No, it looks better now. Sorry about that. Okay, yeah, it can be a bit confusing, like these extra variables. Okay, now it's fine. Okay, so this stuff equals the probability that u is less or equal to u and v is less or equal to v. So oh, and then oops, I should have made let's see. Yeah. This is fine. Oh, did I do something silly here? Ah, okay, I do have to fix something. Oops. So when like the idea was I will write it because otherwise it will be a mess. So when I'm changing the bounds for this integral on the inside. When y tilde is minus infinity, when y tilde is minus infinity, t is going to be minus infinity, that's fine. But when y tilde is v minus x tilde, right? Then t is just going to be v. So this should have been v. No, it's fine. Oh, perfect. Okay, so this is the integral of u plus v equals less or equal to v. Sorry, x plus y. Or v equals less or equal to v. But at the same time, this is just the same as what we had written before. Okay, and so it's basically what you see, what's the relationship between them. I mean, we're almost there, right? Like the bounds are the same. The bounds are the same. So, and then whether this is called, I mean, you know, the constant of integration here, like the fact that this is the u tilde, it doesn't matter. It could have been x tilde because u equals x, so it's not a big thing. So this just means that, you know, that if you compare them, they should just be like, yeah. Okay, I think I will have to require a little bit more explanation. What I'm saying here is that you can call, I mean, you can identify x tilde with u tilde. There's not really of a difference. Like you remember when you do it like an integral, you kind of like the variable of integration is like a dummy variable. So that can be called whatever it needs to be called. And then you can call instead of thinking of t, you can call t the tilde. And so that's why right, that's why then you can compare if you do that, then this becomes, this would become u tilde, and this would become v tilde minus u tilde, which is what you see here. So that's how the densities are related. This I did in complete generality. I didn't do it just for the uniform distribution. So only part B requires a uniform distribution argument. Is that making sense?
So that's the answer for part A.
Correct. This is the answer for part A.
Okay.
I mean, you could like, you could evaluate it for the uniform distribution, but I would say like that's not the fact that they were uniform distributions is only okay. So we can work it out. Yeah, we could do it like, okay, so we could do it in you wanted X and Y were both uniform distributions, right? So but then and they were independent. So let's see, is this like a good way to do this? Let's see.
So you did a change of variables so that we can write everything in terms of u and v, right?
Yeah, essentially it's like, right, it's yeah, so secretly what's happening, okay, right, is that secretly u was X and Y, and V was Y plus X, right? So yeah, you here from there you can say that V minus X equals Y, right? Which is what you did in Calc 3, and then you can say V minus U equals Y, right? So if you see that, what I'm doing here, that's essentially that, right? Basically, I replace X here with U because that's what it is, and I replace Y with V minus U. The thing is that what happens in general, so yes, the densities do get replaced like that. It's just that you have to be a little bit more careful because I don't like this is like, I didn't want to get into this Jacobian. I mean, maybe may have been easier to do it that way, right? Yeah. So perhaps it was easier with the Jacobian if you remember it.
It comes out to 1 in this case.
Right, that's the thing, right? Here you don't see it because it's 1, but in general, if you remember like the change of variables, dv du is Jacobian, or absolute value of Jacobian, times dy dx. The thing is that what was the Jacobian? It was like here, like in which order do you do it? You do like the derivative of u, I think is derivative of
u dx and then
right.
u dy on top, I think.
Well, that doesn't it won't matter too much in that in particular because the determinant is the same as the transpose, so that's fine. But yeah, you can put the u variables here first. I was just trying to remember if it was like the derivatives, if the derivatives with respect to x should be at the bottom or at the in the numerator, and if the usual Jacobian goes like which ones goes in the numerator and the denominator. So let me just check. I mean, like we can work it out in a specific case. So okay, yeah, like the usual way, like right. Yeah. So like the usual way to write it, like is that one is the inverse of the other. That's why you can get confused. Like you can write it as dy dx equals the absolute value of the Jacobian dv du. Okay, that is better. Where you think of so because for example, if x equals r cosine of theta, right, and y equals r sine of theta, then this is kind of like saying that dy dx equals r dr d theta. So that is like right, like the Jacobian in this case, I'm thinking about it as like the derivative of x with respect to u, the derivative of x with respect to v, the derivative of y with respect to u, and the derivative of y with respect to v. If you wanted the other version, it's just like taking, you would have to take the inverse, but it's kind of, that's fine in this case because that's not too big of a thing. So what this is saying is that, right, like, so that should translate to the formula that f of x, the density times dy dx, the version of this is like the density in terms of u and v, making the substitutions. Like, I'm just saying, like here, I'm just trying to say like the density function in terms of like where you replace x as a function of u and v, y as a function of u and v, times the Jacobian dv du. So like, for example, in this case, where like, right, where we found the change of variables like in a second ago. So you can think of x as u and y as v minus u. So what's the Jacobian here? The Jacobian was like the derivative of x with respect to u, the derivative of x with respect to v, the derivative of y with respect to u, the derivative of y with respect to v, and that is 1, 0, minus 1, 1. Right, so this determinant is just 1. Right, so that what that's saying is that the density in terms of x, y, dy dx is the same as the density of xy let's see, u is I mean there's u and then there's v minus u times 1 dv du, and that's how you find that this had to be like you know, this would have been in this case f of uv, but in general f of uv then would be like the density of x times the Jacobian, because then this, all of this junk becomes a density. Okay. Yes. So, but and you don't need to know this formula, but right, it can. I guess on second thought, it is a lot faster. But I think, like for the, I mean, it's a good problem to know. But yeah, you could have done it like from more archaic ways. But yeah, this would also be, you know, I would give, like, if I give you like a problem, this form is like a problem where like one of the variables is still the same, the old one as the new one, so that you don't have to go through the Jacobian stuff, but you can do it if you want to that way. Is that okay? Are there any other questions? Well, maybe while you think about something to ask, I figure I should at least tell you this because it's nice and I feel that I should have mentioned it. So if you just as an, I mean, a useful, interesting aside, if you think about the normal distribution or this Gaussian, right? Like the Gaussian density function or the Gaussian distribution, like however you want to call this, like there are a couple of things, ways to think of how this would arise, right? So one manifestation of it is that it is the limit of the binomial distribution, right? We did that like a long time ago. So one origin of the Gaussian is as the limit of the binomial distribution. We did that one a long time ago, which generalizes to, you know, appearing in the central limit theorem, right? So that's one reason why, like these two are kind of like the same idea, appears in central limit theorem. So like one chain of thought for why the Gaussian is important is that of its relationship with the central limit theorem. Another alternative way to think of why the Gaussian is important is that it is like the distribution or the density function which maximizes entropy, right? So it maximizes entropy amongst the density functions with a given average value with given mean and standard deviation. And that's a different idea. So they're not they didn't have to be related. That it didn't have to be the case that, like, in a sense, the same distribution that appears in the central limit theorem would have been like the same distribution that maximizes entropy. I mean, a priori, the two ideas are not connected. Another third idea of why the Gaussian is important, which is like one I didn't discuss in class, is that it is kind of like is a distribution that has like symmetry, rotational symmetry. So it has rotational symmetry. And so what do I mean by that? So what do I mean? Like, imagine that you have like a, what does this mean? Well, to talk about rotational symmetry just means like how an object looks when you rotate it, right? So, this doesn't have like a pen doesn't have rotational symmetry, because if you rotate the pen, you will get like, I mean, you can distinguish that from like the previous configuration, right? Rotating a pen gives you something different. But if you have a disk, right? If you rotate a disk or a circle about its center, right, you cannot, if you close your eyes, like, you wouldn't be able to tell whether it was rotated or not, right? That's the whole point of a circle being symmetrical, right? So, but like that's a concept that requires two variables, right? Like there's no, if you only live in one dimension, there's not like a good way to say that an object has rotational symmetry. Okay, so in this case, it means that you would have like a density function for two variables. So you have two random variables which are independent. So like that's how you would start here. Two random variables which are independent. So f of x comma y is f of x times f of y. So their distribution, joint distribution is just a product. That, I mean, many random variables are independent, so that's nothing special. The symmetry condition is that this is just a function of the radius. So to the distance to the origin. So the symmetry is that the symmetry assumption is that this only depends on R of polar. So you can write this as a function of R. Well, I mean, it doesn't matter too much whether you write it as a function of R or a function of R squared. They're more or less the same, but for the algebra, it's a little bit easier to write it like it's a function of R. So this is just saying that this density function, it is a product of the individual, the joint density function is a product of the individual densities, but at the same time, the joint density function only depends on R, where R is, the coordinate from polar. Okay, so you have this equality that f of x, the density of x times the density of y is f of r squared. Okay, and so the question is, what functions could satisfy? Here there are three functions, right? F of x, f of y, and f. There are a priori three functions, right? So which functions satisfy this equation?
With e to the negative x squared. It
Right,
satisfies-
correct. Although that's what we need to prove now, right? So, but like the cool thing is to prove that that's the only one that satisfies it. So yes, correct.
That's what 3 Blue 1 Brown's video was about, right? Where he
Correct,
talked
that's
about the-
like, yeah, this is like the Maxwell-Herschel derivation of the Gaussian. Apparently Herschel was just trying to figure this out for a problem about throwing darts. Well, but then like, surprise, surprise, that's how it appears. So it's kind of funny how many of these probability concepts just started just for me, people wasting their money gambling, right? Like, it's kind of weird that that would have like so many consequences for like the development of mathematics. But because like the Greeks were not interested in like, the ancients kind of like had like a notion of chance, but it was not really until the Renaissance like you could actually collect a lot of data. And then you think about statistical methods and other things. So that's why the developments of probability are a lot later compared to many of the other branches of mathematics. They just had their philosophical points of view were not like kind of appropriate to develop it. So so one thing you could do is that you can take the derivative on the partial derivative on both sides with respect to x. Okay, so what does that give you? I mean, I'm putting like a partial derivative here because like this expression depends on both on x and y. Now, if you look at this gives you the derivative of, I'm going to stop writing the input because otherwise it will drive me crazy. So, well, who cares? I will keep writing it. So how can you find the derivative of this? This depends on r squared, right? But you can take its derivative with respect to x because of the chain rule for multivariable calculus, right? So if you remember how this chain rule went, this one is actually very easy, but it's just like f dependent on r squared, but r squared, if you like these three diagrams, but r squared depends on x and y. So the derivative of f with respect to x is just the derivative of f with respect to r squared. Well, this is where like, okay, this is where I may go back. It doesn't really matter too much if you are in terms of r or r squared, but it just looks a little bit better maybe when you take this derivative to just write derivative of f with respect to r times the derivative by the chain rule times the derivative of r with respect to x. Is that making sense? So that's what you get. And so this gives you the derivative of f of x. What is the derivative of the partial derivative of r with respect to x? That's well, r is root of x squared plus y squared, so it's not too bad to find. It's basically that, right? Because yeah. So this is x squared plus y squared to the 1/2. Right, the 1/2 comes down, and this becomes minus 1/2. This becomes minus 1/2, and so that's what you get, like the square root in the denominator. So, but that's like just the same as r. And then there's a 2 from the chain rule that cancels the 2 from the 1/2. So that gives you that. Okay. And then let's see. So you can rearrange this to say that 1 over x, the derivative of f sub x dx times is times f sub y is df dr times 1 over r. Okay. So far, so good. Are there any questions about this up to this point? So we find this is the first thing that you find. There's nothing that really changes too much if you do the same with the derivative with respect to y. So by analogy, taking partial with respect to y, if you had taken the partial with respect to y, taking partial with respect to y instead, what do you find? You find it is the same, but with y. So it's 1 over y times the derivative of f sub y dy times f sub x of x is df dr times 1 over r. Okay. So it's completely symmetric calculation because x and y appear in the same formula, appear in the same way in the formula for r. So you just change the roles of the x's and the y's when you find this. But what do you notice between these two equations? Like what you can notice is these two sides agree, right? They're the same right-hand side. So that forces 1 over x, the f sub x dx, f sub y, to be 1 over y, the f sub y, 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 f sub x, x. Okay, and then let's just move the stuff that depends on x on one side and the stuff that depends on y to the other side. So this is just... Is that okay? And now, well, this is just a function exclusively of x, and this is like an expression exclusively of y. So how can an expression that depends only on x equal something that depends only on y? The only way that for that to happen is actually if each of these is independent of the variable they're supposed to depend on. So that actually forces, right, that actually forces each of them to be equal to some constant. Okay, so this forces this to be constant, each side equal to a constant independent of the variables. So for example, that means that 1 over x, the f sub x dx equals constant. Oops. And this is like a ODE if you took differential equations. So I mean, this is like not that different from like the ones that you would solve in, even in Calc 1, you could have solved something like this. So you would write it like this way. It's similar to what you would do when you were finding potential functions or things like that. So you get cx dx. Okay, and when you integrate on both sides, right, integrate both sides here. And so that you get ln of f sub x and then cx squared over 2 plus like another constant, like you can like, okay, let's just put like plus some constant or whatever. Like the important thing is that this constant of integration, it doesn't matter too much. Like the important thing is like when you take e to both sides, that's how you get like the exponential term. The only thing, right, it's going to be like some constant times, okay, this constant will look, let's call it a. Okay, this is roughly the Gaussian format. It's just that this constant has to be negative for the density to, you know, actually, I mean, you do want the density, you want the integral to make sense. So that will force the constant to be negative. So that's where, you know, you can just play a little bit. And like the standard one would be when you take c equals -1, right? And then a, what is a? Whatever it needs to be for that to integrate to a probability density function. But yeah, so you conclude here from that c must be negative for the integral to have a chance of making sense. To make the for like the density to, you know, to make this function integrable from -infinity to infinity. And so the standard one is just when you take c equals -1 and a 1 over root of 2 pi or whatever. But it is a very clever argument, and this makes it less mysterious. Again, if you watch this 3 blue 1 brown video, it does also make it less mysterious for why there's a pi that appears like you know. What this is saying is that this is 1 over root of 2. I mean, the basic one is like this one, right? And the same idea would be for like the. This makes it less mysterious for why there's a pi showing up here, because this distribution is related to to circular symmetry or to polar symmetry. It is related to circles because it does depend. If you look at it at a 2D version, is the only one that depends like essentially on the radius. Okay, so that's why it's not like mystical that a pi would appear, because a priori, it's kind of always funny when E and pi come together, right? Because they seem like constants which are defined in very different ways. So why should they be related? But it makes a lot of sense, like from this perspective, because this distribution is really related to having circular symmetry. So, and then there's like a spherical version of this, right, in 3D, where like the density function for X, Y, and Z factorizes as a product, and then it depends on the row from spherical, and it's more or less the same idea. It would have to be like a product of Gaussians and things like that. But so like the point is that these Gaussians are really very closely tied to being symmetric in a rotational sense of the word. So it's like a good, again, it's like useful to have like different ways to think of why the distribution would appear. So one is because of the central limit theorem, the other is because of the entropy principle, and the other is because of a symmetry principle that it has like this, it respects these polar symmetries. Is that making sense?
I had a quick question.
Mhm.
Why? I think you kind of showed it with like the proof above, but I was just curious why it's e to the negative x squared over 2. That's like the standard one. Is it because of like the standard deviation of 1, or?
Right. It's just, the advantage of having, okay, the mean being 0, that kind of makes sense, right?
Mhm.
And then why would you want the standard one to be with standard variance 1? The thing is, like, if the variance, if the mean is 0, then the variance, like, the thing is like 1 equals 1 squared. That's
Yeah.
the way of saying it. So it's kind of
Okay.
very convenient for the standard deviation to be normalized. That's actually what the normalization always means, right? Why do you want like unit vectors also? Like, it's just like 1 has so many useful properties in terms of multiplication, right? Because it just gives you 1 and 1 and 1. So right, it's just useful to take the standard one to have standard deviation of 1, because then when you square it, what's the variance? It's just 1. You don't have to think, you have less chances of making mistakes. And also, like, right, it's just because of all these rescaling properties. So yeah, there's nothing, it's like a very natural choice because of those reasons. But yeah, like in many quantities, it's just useful, to normalize things so that like unit vectors, orthonormal basis, like this stuff with the densities, probably even the probabilities. So the probabilities being between 0 and 1, that is like a reasonable convention. If you think of this in terms of frequencies or ratios, because ratios like arbitrary 0 and 1, if you think of them as counting like number of successes over total experiments, right? But this is why sometimes probabilities are given also in terms of percentages, right? Like so many times instead of saying 0.5, you would say 50%. So there's nothing magical about the probabilities being between 0 and 1. If the probabilities had been between 0 and 3, then there's like a simple rescaling, that would have taken care of everything. There's like always like a way to retranslate that into being between 0 and 1. But it's just so much useful to, probabilities being positive, that does make a lot more sense. Because again, if you think about it, like coming at it from like the frequency perspective, where probabilities represent some limit of frequencies, which is a little bit more complicated than that, but then that it does make that at least you would always want the probabilities to be non-negative. But the fact that the probabilities had to be had to go up to 1, again, it makes sense from the frequency stuff, but it would have been easy to fix, if someone worked with probabilities up to 5. What you do, just divide everything by 5, and then you get, it would always be easy to translate them. So it's just like many times it's just so useful to have 1 and 0 appear in the formulas, because like that simplifies a lot the calculations. Is that making sense? The other thing, I mean, just in that spirit, like, you know, if you write like this formula. Another useful thing to notice, like, you know, probabilities are pure numbers, like in the sense that probabilities are always dimensionless. That's useful to know. So probabilities are always supposed to be, you cannot say probabilities are 10 meters, like you cannot say your probability is 0.1 meters. That's not allowed. Probabilities must always come out dimensionless. It is similar to, like, you know, sine. You cannot say, or like E, you cannot say E of 0.2 meters. Like in an exponential, you can only put dimensionless numbers, right? The argument. So since this has no dimensions, if the random variable has dimensions, then that means that the density function must have dimensions of the inverse of the random variable. So it's kind of also useful to know that the units of the density function, so the density functions are not dimensionless. It's 1 over the units of x. So that way, this times this multiplies to something dimensionless, and then you can just get a pure number for probabilities. So that's another useful remark. I mean, not that we work too much with units in this course, but it's kind of like, that's the same reason why we talk about the standard deviation, so that it would have like the same units as x and things like, and not the variance, because the variance has the units of x squared, for example. Are there any other questions?
I just wanted to ask for 81. You know how in part B it asks us to solve for sorry about taking a sidetrack, but on question 81, it asks us to like actually compute like the density, like I think the density.
Right.
And you said we're gonna use a convolution, right?
Correct.
And you said we're gonna use the fact that they're independent and they're Bernoulli variables.
Right.
And they're uniform. Right.
Correct. Yes. We can go back to where we had that calculation before, just to show it again. Right. That's a good remark. The convolution formula only works when x and y are independent. So that's important to keep an eye on. Let's see. Oh, like I think the convolution I found it after. Oops. No.
Couldn't we do like put the density as 1/4 since it's like Bernoulli or something?
Well, okay, so you have to be careful. Like the name Bernoulli is just reserved to the case where the random variables are discrete. The thing is, like, these, like, oh, here it is. These take values, in principle, can take any values between 0 and 1, right? Not just 0 and 1. So it is not quite a Bernoulli function because, you know, I mean, you can have uniform discrete distributions and then take their convolution, that's fine. But that's a little bit different here from what we have here, where, you know, the random variables are continuous. Does that make any sense?
Oh, so we can't divide 1 by the area.
Oh, well,
Can't do that.
like the thing is, like, yes, you cannot, well, for 2 reasons. Like the first one is like, it would be more, right, like the uniform distribution for 2 variables, like the thing, okay. How should I say it? So, okay, so there's okay, I see where, I think I know what the Yeah, I think I know what you're trying to ask. So yes, if you had like right, if you have let's say a rectangle, let's just make it a rectangle to make it easier. Um, this rectangle from A to B, and here's A, here's B, and here's C, and here's D, right? If you have a rectangle like this, you can take the uniform distribution on this rectangle, right? What is the any uniform distribution of this rectangle? The uniform one is 1 over the area, right? Which is what you're saying. So B minus A times D minus A, D minus C, right? When, you know, X is between A and B, and Y is between C and D. Right, so that is a uniform distribution into variables, and when the uniform distribution into variables is on a rectangle, then X and Y are the right. So this means that f of X comma Y will be f of X times f of Y, where this is just like, 1 over B minus A, right? And this is 1 over D minus C. So that the uniform distribution on a rectangle is the product of the uniform distributions, on the intervals. But here, the thing is like the density, right? Like the density for UV, right? It wasn't just the product, right? It was not just the product of the individual densities in the independent case because of this shift in the argument. So that's why it's not just like dividing by the area, if that makes sense. Because it's not f of u comma v. If it were like f of u comma v, then yes. But the thing is like the second argument like involves the first, kind of this also depends on the value of the first one. So that's why it's not that's why the sum, like the sum of the random variables is not just like kind of like the uniform, it's not just like looking at the area or something like that.
Oh, because part B asks for the compute the density function of V.
Right, of the sum, right, of V being the sum of the random variables, right? And that's the one that has the distribution being the same as the convolution, right? It's just that this convolution thing is not just the product. It's not the product of the densities because the argument, right, is not like the same at the same, it's not at X and Y. Is you have to do this like shift of one of the two variables first. So this is like this is the one that I was saying that f of v is a better, so it's like the minus infinity to infinity. So it like if you look inside the integrand, it is a product, but it's just that one of the arguments was shifted. So that's what messes up that's what messes up the comparison with just like the uniform distribution of two variables. Yeah. Is that okay?
Yeah, it makes sense.
But right, in all these problems, again, like I'll make sure to write it explicitly that whenever like the random variables are independent or not, but many things just do not work of what we have done if the variables are not random. So it is important to have random variables, which are, sorry, the variables are not independent. So it's important to have like independent random variables for many arguments to just go through. Otherwise, anyone else? Any other questions?
And then, so you just take the integral of this, right? If you're finding.
Correct, right, and yeah, and then that's exactly the same that we did in class before. That's on the day that we discussed the law of large numbers, just in case. So if you want to check the calculation again, you can. I did it in that day, but yeah, it is doing the integral for that.
Also, we don't even have to solve for the probability, so this is basically it. Right?
Right, it's just a density, correct, yes. The other thing that I was, I mean, like, which is like a good remark to make because I forgot. So there's this problem 87, which you can ignore. I had mentioned it on the PDF, but you can ignore it. Ignore it. It was like about showing that the variance in square, like that the square root of the sum of the variances is less or equal than the variance, the square root of the variance plus the square root of the variance. Oh my God, I'm saying this terribly. That if you take the variance of a sum in square root, that's less or equal than the sum of the square roots of the individual, the sum of the square roots of the individual variances. The thing is that I never got to tell you this requires something that's called the Cauchy-Schwarz inequality. So you can ignore it because it requires Cauchy-Schwarz inequality, which we didn't discuss, but at least I can tell you what it says because it's a useful inequality to know that it exists. So if you remember, like when you have two vectors, like I can write it like, so what does this say just for you to know? If you have two vectors, like let's put like the vectors with 3 entries because that may be the stuff that you remember from Calc 3, right? So what does the Cauchy-Schwarz inequality say here? It's, I mean, what was the dot product between these two vectors? One way to think about it, like, is that this is like the length of v, sorry, the length of u times the length of b times the cosine of the angle, right? So if you look at this formula, let me see how I want to write it. So yeah, if you look at this formula, this is always yeah, this is always, I mean, because the cosine is always less or equal to 1, this is always less or equal to length of u times length of b. So when you have a dot product, the Cauchy-Schwarz inequality for vectors is just that thing that you see here, is that the dot product of u dot v is less or equal to length of u times length of v. Which looks a little bit silly. The thing is, like, the way in which this is actually done in a proper course is that you kind of prove the inequality first to show that you can define the cosine of the angle using the dot product. So it's like kind of, you have to really turn things around to how it's maybe usually introducing, like, the preliminary courses. In fact, it actually looks a little bit more interesting if you write it in terms of the entries, because what this is saying is that the UIVI, right, this is like the formula for the dot product when the vectors have n entries. The length of this would be the square root of what is the length of a vector of the sums of the squares, and you take square root of that. Right, this is what the length of b is. This is what the length of u is by Pythagoras theorem. You square the entries and add them together, and they take the square root of that. And then you square this one and add them together and take the square root of that. And if you write it that way, then it looks a lot more intimidating, right? So it's not like I mean, it's not like a difficult inequality to prove, but it's also not like, I mean, it looks a lot less silly if you write it this way. The thing is, like, there's like a version of this for integration. So there's like a version of this for integrals. Which says what is the analog of a sum is an integral. So it says that if you have two functions, I mean, you could put them, I mean, you could put it like from A to B or whatever, like, or it could go from minus infinity to infinity. You just have to make sure that, like all the integrals make sense. But it says that if you have two integrals, if you have two functions, you multiply them and you integrate them, which is the continuous analog of, that's actually the continuous analog of doing the dot product, just like an integral of a product. So that like the version of the Cauchy-Schwarz is actually, this is less or equal to the square root of the integral of f square of x dx times the square root, the integral from a to b of g square of x dx. Okay, and so that is eventually what so this is actually, you would need like an inequality of this form to, which we didn't cover, so that's why you don't have to worry about this problem. But you would need like knowing an inequality of this sort, because something like that will be something like that will be needed when you prove like this inequality for the variances. What's interesting here is that is what allows you to actually define like a dot product between functions, which is actually called the inner product. The people don't call it dot product. So the dot product between functions. I know one uses this notation, but it would just be like the integral from a to b of f of x, g of x dx. And then you can say that two functions are perpendicular if their dot product equals 0. And that's how like this Fourier series comes from, because the point of the Fourier series is that sine and cosine are kind of like an orthonormal basis for the vector space of functions. So like that's like the idea of like more or less the idea behind like a Fourier series. So f two function sorry, I shouldn't even put like dots here, but I was trying to emphasize the idea that you think of the functions as vectors. So two functions f of x or g of x are perpendicular or orthogonal. If their integral integrates to 0. And that's kind of like the same. That's the idea behind like the Fourier series. Which I'm sure, like if you go to 3 Blue, 1 Brown, there are like very good videos about that. But that's basically it. But yeah, so like this problem, I accidentally included it in the list of problems to look at for the final, but you don't have to worry about that one because like it involves the Cauchy-Schwarz inequality. It's just that, let's see, just give me a second. So the version of that ends up being useful, like the version in probability, the way in which it's written, is here. It's on the book, but it's like the way in which the book usually writes it is like or the probability books, because like the integral is computed like an expected value. So the way, let me see if I have it here. Right. Yeah, so like the version for expected values is that the expected value of xy, there's like a version for expected values you can find, is something like this. Like I'll put just to make it more look closer to this, like it'll be like, well, but maybe hopefully this maybe this looks a little bit more it looks less weird why this might be true if you believe that something like this is true, because the expected value of a product is more or less like this. You just have to multiply by the like the density functions or whatever, but so it does require a little bit more it's like more or less the same proof, but I'm just saying that there's like a version of Cauchy-Schwarz for expected values, which is like the one that usually gets used in probability theory. But again, you don't have to worry about that. I just thought I should mention it because at least I had included that one as a problem on to look at for the final. So don't worry about that. Yeah, I'm not sure. Like, are there any other questions? Okay, well, let's say, in any case, if something else comes up, feel free to email me between now and the final. I think I have to still write like the solutions for one of the for the last assignment, so I'll write it. I'll try to write it today and send it to you so that you have a time to check it out before the final. But yeah, like, I'll be around if something else comes up, but just pay closer attention to the new stuff we did after the second midterm. That's where the focus of the exam will be. Look at all the examples that we did in class. Look at the examples that the problems that I recommended on the Gradescope assignments. Look at the practice exam, extra problems, and just try to go over as many as you can from the PDF, but I would go in that order. Examples in class, followed by assignment problems, followed by practice exam problems, followed by whatever is left on the PDF problems. So, but if you do that, I think you should be fine. But yeah, if something else comes up in the meantime, feel free to email me. I'll try to answer it. So I think, yeah, we can end it here if that sounds good.
Professor, I had two quick questions.
Yes, yeah, sure.
One from, it's like one from each of the first like practice exams for the first exam. I don't know if you have it pulled up. I know there's one where it's like an examiner sets 12 problems, and then
I
like
have it
one of
here.
the students memorizes 8 of them. So
Oh,
I was
right.
at the solution, and like I know it's like a function P of R is equal to, and the denominator, that makes sense because it's like 12 choose 6, because that's like
Right.
the amount of options. But I wasn't sure like how they exactly came across like the numerator of like 8 choose R multiplied by like that 4 choose 6 R.
Let's see. Okay, let me see. Okay. Oh, I think I got it. Let me just read it. Like you have 12 problems, and you tell the class that the exam will consist from 6 of them selected at random. Oh, okay. So what is the chance that he gets 4 or more correct? I think it's better to just think about it. Let's give like a concrete value to R. Let's see.
Do like P of 4, for example.
Well, let's do P of 3 so that it looks less trivial, right? Like, so what are the chances that he gets 3 correct problems, right? So what is 8 chooses 3 in this context? Like 8 is like the, okay, it's kind of like you're looking at, okay, yeah. Let's see. You're looking at 2 things at once. Like you need let me write it down, like see if I can remember. So an examiner sets 12 problems and tells the class that
Yeah, it looks like the answer, what they're doing is they're multiplying like the ones he knows, like the ones that are from his memorized list,
right.
with ones that he doesn't have memorized.
Right. Because okay, if you okay, the thing is the way in which the problem is set up is like if Gavin sees a problem he doesn't know how to solve, it just seems like he will he will leave it blank. I think that's a better way to think about it.
I see. Okay.
It's not that he's going to write something random and by luck he'll get it right. it looks more like the context is more like he will, and maybe you should have said something like it will, if he sees like a problem he didn't memorize, he will not write anything.
I see, yeah.
So in that sense, like, right, for him to get 3 problems correct, you must, like, these 3 problems would only come from the 8, right? Can only come from the 8. So that's where like the selection from the 8 chooses 3 comes from, right? But then like yours, you are splitting the 12 problems into 8 and 4, right? Because 8 are problems that he can memorize and 4 are problems that he cannot memorize, right? And so you know, if he can, like, you know, for him to get 3 problems correctly, those 3 problems had to come from 8. That's why there was this 8 chooses 3. And then you know, in the exam there would be like 3 problems left, right? So that's where the 6 minus r comes from. And then you are choosing like you know, those 3 those 3 remaining problems that he will leave blank are coming from the 4 remaining ones. Is that making sense?
Oh yeah, that sort of makes sense. When I did it, I kind of just like I did it naively. I just did 8 choose 6 plus 8 choose 5. I didn't multiply it, but I think I can like reason why you would do that.
It's always like in these problems, like maybe sometimes it's usual. My rule of thumb is kind of like just drop down the numbers significantly. So instead of
Yeah.
like 12 problems, let's just say, well, let's say 5 problems, and let's say that he memorized 2, right? And the exam consists of you know, of 3 problems or something like that. So everything you can really kind of go through the entire list.
Mhm.
If you choose, in fact, you can even make it more extreme, like, you know, like only 4 problems in the exam and he memorized only 1 or 3 or whatever, like, you know, just to have like just to make like, yeah, because that's actually one of them. Like, if you have noticed, like probability is kind of like if you don't know if you're not sure which arithmetic operation you should use, it is like a better chance that it would be a times than a plus.
Hmm.
You know, almost all the formulas, if you notice, involve like a multiplication somewhere, right? Very few problems are just adding up probabilities, like in
That's true.
or like or adding up these combinatorial things. So if you have to make a guess, it is a better guess to, like, if you don't know anything else, like most of the probability formulas involve some sort of multiplication, you know, especially at the beginning where all these combinatorics and stuff. Yeah.
Let's see.
And there was another one you wanted to ask me, right?
Yes, this is from is it this practice exam 2 for exam 1?
Okay. Let's see.
It was with the 6 physicists and the 7 mathematicians being paired off.
Oh, right. Practice exam problem 2. Oh, but exam one, right? Still.
Yeah, it's
yeah.
exam 1 content, but it's the second practice exam.
Right.
Yeah, so I did sort of like a, I mean, the explanation actually, it kind of made sense, but what I did was a little different, and I was just like not exactly sure what was the flaw in my logic. So I actually did what you said. I looked at a smaller case, and I
Right.
came to the conclusion that there's going to be like 42 different possible pairings of like the mathematicians and physicists. So like 6 times 7. And then for my answer, I put 42 choose 4 because I thought that, okay, out of these 42 possibilities, you're just choosing 4 of them.
Okay. So what were the numbers that you chose?
For this one, the 42 choose 4, that's like the actual case, but I tried looking at like a smaller case where there's like 3 mathematicians, 3 physicists, and then
Okay. So you're doing 3 mathematicians and 3 physicists, right?
Mhm.
So let's call them M1, M2, M3, right? And P1, P2, P3, right?
Mhm.
Okay. And then, okay, so you do need like, you know, I guess it's one of, right, it's one of each, right? Like the parents, I suppose, right, it was like each pair should be consisting of 1 mathematician and 1 physicist, right?
Mhm.
So, I mean, it doesn't make sense to like the, you know, the easiest thing would be to, you know, let's say that there are like 2 pairings that you want to make, right? So how many are they possible? Let's see. Okay, so right, like one way would be like the naive. I mean, how is it that you wanted to do it in this example before? Like, I don't want to look at the solution just to see if like I know
Sure.
how wanted to try to do it.
Yeah, so what I did is I just like I list them all out and I noticed you can just do like M1 with all the physicists, then M2 with all the physicists. So it's just like a square. You just have 9 possibilities of pairings because I considered like M1 P1 the same thing as like P1 M1.
Right.
And-
So yeah.
So there's 9 possibilities, and then from that I just said choose 2. So my final answer in this case would be like 9 choose 2.
Oh, but okay, let's see. The thing is like the two pairings have to be made at the same time, right? So like for example, okay, I think I know what
Ooh.
you know what okay, right. It's not
Let's see.
it's not what you're really going to set because we're making two pairings, we're kind of selecting 4 people at the same time, right? So it's not that you're making just pair like couples,
Yeah.
right? That's the difference. Yeah, so it's kind of like you are selecting 4 people at the same time. It's that 2 have to come from physics and the other 2 have to come from mathematics. But it's not just like a square, because a square is kind of like not taking into account that, you know, if one pair is like physicist 1 with mathematician 1, then physicist 1 cannot appear in the second pair that's being made at the same time, right?
So like in this case, the first one you'd have 9 options, I think, and then the second one you'd only have like 4, I believe.
Now in this one you mean for like 3 and 3?
Yeah. Is that
So
true?
okay, let's see. So yeah, so for the first pairing, let's see. For the first pairing, I could choose any 3 physicists, right?
Mhm.
And then any 3 mathematicians, right? And then I think we will have to divide at some point because we're over counting. But once you made a choice of a physicist and a mathematician, the second pairing cannot use them again, right? So it's 2 and 2, right? It's just that it has to do. Okay, the thing is like it has to do with this combinatoric symbol because this is not the right number, right? It's not 3 times 3 times 2 times 2 because we have to take into account by the fact that you don't care like the order in which you chose them and things like that. And that's why the formula ends up being similar to the right to the one that I wrote. But yeah, if you focus, if you compare this to the formula that I wrote, like for this version, it would be 3 chooses 2 times 3 chooses 2 times 2 factorial.
2 factorial.
Right, and that what is 3 chooses 2? Oh my god, this is that just 3? What is?
Yeah, I think so.
Yeah. No, wait to see. 3 chooses 2 is like 3 factorial, right? Oh yeah. 3 factorial over 2 factorial, 1 factorial, right? And so that's just 3. And so this is 3 times 3 times 2. Okay, right. So that is what this is 18, right? Let's see. And then how does it relate to this? Okay, right. If you just did the naive multiplication of these numbers, right, you get 3 times 3 times 2 times 2, which is 36, right?
Yeah.
But then you have to divide by 2 from the fact that you don't care about the order in the first pair, and then another 2 from the fact that you don't care about the order. Oh, wait, no. Now am I doing like am I getting 9, right? Take this.
Would it be dividing by like 2 factorial maybe?
No, but 2 factorial is just 2.
Because it's also 2, but I'm
right.
wondering like the more general case if that would also work. I'm just curious.
Oh, let's see.
Is that
wait.
what-
Or let's see. Oh, okay, no. I think it's just okay. No, it said so you have to be careful here. It's not that you are dividing just by a single two because you don't okay. Like you right, it's like it is better to actually write everything down. I mean, it should just be 18 cases, so you'll see what happens. Like, yeah, you can do like it is like you would think, well, it's like 3 times 3 times 3, 3, 2, 2, right? But so that just means it's like physics 1, M1, right? And once you do that, like the other one could be like, physics 2, like, M2. That's like a possibility, right? Here's the thing. Like the thing is like these are kind of like different entities, right? Like the physics, so it doesn't make a lot of sense to swap them. You have to make a, when you list them, you can make a convention that's unambiguous to say I will always name first a physicist followed by the mathematician, right? So the
Mhm.
swapping is not occurring here. There's no swapping between the two entries. The swapping is kind of between the two groups, right? Because it represents the same two pairs to list first like the members of group 1 followed by the members of group 2, or members of group 2 followed by members of group 3. So what I'm trying to say is that these two do represent the they are being counted they do represent the same two pairs. Is that making sense? So think of the pair as a single unit. I think that's a way better way to put it.
Trying to do some calculations and see if there's any way to salvage this one.
Well, right, but yeah, it's better. It's still better to kind of make it all explicit. But I guess like in fact, like you could make it even right. It's that it is convenient to have at least right. I think
I found something that works, but I don't know if it's just like a lucky coincidence. So I did like this sort of the same thing that we did before, where it's like 3 times 3 times 2 times 2 divided by 2,
Mhm.
and that ends up working. So I did the same thing for like the general case, where I did like 7 times 6, then 6 times 5, and then you just do that like 4 times, and then I divided it by 4 factorial, and that also got the right answer.
Okay, let's like what I'm saying is like let's just do it with three physicists, 2 mathematicians. So the formula it is a little bit more simple because it would be like that should just be what it should just be 6. So it should be fewer cases. So how many pairs are there? Like if you wanted to make 2 pairs at the same time, right? Like you could pair P1 with M1, right? Once you make that pair, you can pair also P2 with M2, right? You could also pair P1 with M1, but also P3 with M2, right? So those are 2 allowable. Then you could also pair, you could also pair P2 with M1, right? And then you can pair P1 with M2, or you could pair P2 with M1, right? And then you could pair P3 with M2. Is that making sense?
Yeah.
And then you could pair P3 with M1, and then you could pair P1 with M2, or you could pair P3 with M1 and P2 with M2, right? And I think these are exhaustive because yes, these should be all the pairs because I was just going like the first P with the first M and then just like filling it out. So I think I'm not missing anyone. It's just that what the way to think about this one. I mean, you can think it is better to think of them as like the first and like think of it as an ordered pair where the first entry is for physicists and the other for mathematician.
Mhm.
So it's just that you have to specify like the order pair. So you had like you know, you had 3 options for the first coordinate, 2 options for the second coordinate, right? That was for the first pair. And then for the other one, you have 2 options for the first coordinate and 1 option for the second coordinate, right? So that would give you, 12, right? It's just that this, like, it would have been the same pairs if I had flipped these 2 entries. I mean, if I had flipped the order pairs themselves, which I never did, so that's why I didn't overcount. But what I'm saying is that this configuration is equivalent to P2 M2 times P1 M1, right?
Mhm. Yeah.
And so, yeah, but yeah, all this I must admit that like these combinatoric problems, always give me a headache as well. It's just
That's
like
true.
it's just like a mess. There are people who do like them. I think they're fun, but like yes, I always found them a little bit confusing. I won't
Yeah, I
lie.
think the overcounting, like that actually made a lot of sense, because I was really confused why my answer was so off. But that makes a lot of sense that once you choose one of them, you don't actually have all the remaining options.
I'm definitely not going for something as combinatoric in flavor like these earlier problems, but uh I'm just don't like something like the Bayes rule and things like that. Yeah, I mean some very basic things of combinatorics, yes, but not something too clever. I'm not interested in putting like clever problems from like combinatorics. I don't like, I mean, kind of one has to go through them, but for me it's kind of like a painful part of the course. Like you want to get over it with it. But yeah, at least like the permutations combinatoric, like combination symbols and things like but it won't, if there's any combinatorics, it won't be nearly as hard as some of the problems on the first practice exam or things like that, because yeah, they are like well, the funny thing about that is that like you can actually be like a teenager and solve very hard combinatorics problems. So it's kind of like funny how the brain is just wired for some humans, to be good at this without like a lot of knowledge. But I always found this discrete mathematics a lot more confusing than like this is why number theory and all this stuff sometimes can be very hard, even if the problem, because it's like a problem that everyone without a math education can understand. But when you go down the details, it is very easy to make a mistake. So yeah, they are kind of like mysterious why they are so difficult sometimes, despite their statement being so easy to understand. I don't know. But yeah, no, it won't be if there's something like, it would be very basic. So you like, it's like, yeah, it started like from the beginning of the course towards the initial part of the course, in terms of prioritizing stuff, because I'm not going to emphasize that much this older stuff. Okay, but yeah, but I'm glad you asked me this because right, it has been a while since I had thought about this stuff. So like feels like an eternity ago. So, but okay, yeah, no, if something else comes in the meantime, you can email me. But just start with the new stuff first, and then you can go over the practice older stuff.
Sounds good, Professor. Thank you very much.
Sure, no problem. Okay, good. Okay, yes, I'll see you. Bye.